Hello, everyone. Welcome to the binary episode of the Day Zero podcast. I'm Spectre. With me is Z. No spot the vuln solution to cover this week, so that might be a bit unusual. We were unfortunately a bit late on that, but we will have one again next week. So, yeah, we'll just jump right into topics,
Yeah,
I suppose.
assuming I remember it next week.
Assuming you remember it next week, yeah. So, up for our first topic, we have the vuln of the week, probably the vuln of the year candidate, Dirty Pipe, which is the new Dirty Cow of 2022. It's a Linux kernel bug that has existed technically for like 5 or 6 years, but it's only really been exploitable since kernel version 5.8. So multiple changes kind of built up to allow this issue to exist in a security context. So that'll be fun to get into. But it basically allows the same kind of attack that Dirty Cow did. You get the ability to overwrite file contents in memory, even if that file is technically opened as read only or whatever. So it's that's a pretty easy privilege escalation vector. So
Yeah, you get that. It also is one of those things that because you're corrupting it in memory, it may or may not, depending on the file and stuff, may not end up getting written back out. So it is also a little bit stealthy in that sense.
yeah, for sure. So before we get into the vulnerability too much, I do want to talk a little bit about pipes for anyone who hasn't used them because I mean, let's be honest, they are kind of a pain in the ass as far as IPC mechanisms go. There are easier ones to use, but they are very performant. But at its core, pipes are somewhat straightforward in how they work. Um, and they're present in Linux and other operating systems. There's two types of pipes that are common, being anonymous pipes and named pipes. Anonymous pipes are unidirectional, where one thread or process or whatever has a handle to it and defines itself as the write end. The other end of the pipe is a read end. The writer process can push data into the pipe and the reader receives it. Fairly straightforward. Named pipes are facilitated through the file system and are bidirectional. So one client can push data and another client receives it in a first in, first out fashion. Mainly, though, for the purposes of this post, it focuses on anonymous pipes, which are the more common type. So in the kernel, pipes are basically implemented using a ring buffer of pipe buffer objects, which contain some various things like flags as well as a reference to the memory page for the backing data. So basically, it's like a metadata type of object that's stored in the ring buffer. In normal cases with a pipe, whenever you write some data, the kernel will allocate a backing page for that data. And then if you try to write more data to the pipe, it'll attempt to append into that existing page as long as there's room. If it needs another page, it'll allocate one, but it tries to reuse the existing page for obvious performance reasons. Um, what's important for this bug, though, is there's a different way of getting data from files into a pipe, being the splice system call, which is used for moving data between two file descriptors without actually copying the data. It's kind of again like a performance focus thing. To do that, it'll load the file content data into the page cache, and it'll create a pipe buffer entry that points into that page cache. But this is kind of a special case that has to be accounted for because the pipe doesn't actually own that page. That page is owned by the page cache, so it can't try to append data onto that page because it could end up overwriting the contents of the file or whatever else is in the page cache. Um, which would be memory corruption. It's an issue. So they have to keep track of whether or not a pipe buffer can be merged, is the terminology they use in the kernel, or appended to. For a long time, this was managed in a struct field called can merge, which it worked fine. But then later on, in a later commit, they refactored it and they introduced a flag called pipe buff flag can merge, and removed that struct field and instead used the existing flags field, which was already there. Um, which seemed reasonable. Like that, that makes sense as a refactor. But the problem is a commit in 2016 introduced two functions which are used by Splice to allocate the pipe buffer that it uses, being push pipe and copy page to iter pipe. And that would allocate a pipe buffer from the ring, but it wouldn't initialize the flags field, leaving it uninitialized. So basically, anyone who sets up some data that would line up with like stale heap data or whatever, or sorry, stale data in the ring buffer, could gain arbitrary control over those flags. At the time, that wasn't really a security issue. Like it was a bug, but it wasn't a security issue because those flags weren't used for anything of vital impact. But now, when this other change was introduced, when they moved the can merge trait into a flag, it's possible that those flags can be corrupted so that a pipe buffer page that's owned by the page cache can have data appended to it, and thus allow corruption of the page cache. That's what happened in this case, where the bug was discovered by accident because of this nasty bug that the developers of CM for All had to deal with in their log server. Their log server would use the splice system call to send compressed files and write a zip file, because they had like daily log files that they had a routine for pulling. Um, and occasionally, the end of the log file in the pipe, which had a CRC32 checksum of the file, was corrupted with data from the central directory file header for the zip file. Basically, they were writing a zip header, using Splice to send the compressed files, and using the write for the central file directory header. Um, but if the stars kind of aligned and the uninitialized flags were set to that can merge flag, it was possible for something later in the pipe buffer, in this case, the central directory file header, to smash data from the splice call earlier on in the pipe. So that's basically the scenario that you can use to exploit this bug. You create a pipe, you basically poison the ring buffer so that the can merge flag is set on all of the entries. Drain the pipe, then you splice the data from the target file into the pipe just before a target offset, and then write whatever corruption data you want to write in there, and that data will then overwrite the cached file page. So it pretty insane bug, and it's all because of a silly uninitialized use bug that was committed 6 years ago. So there's a very interesting history for this vulnerability, and it's kind of funny because it was discovered completely by accident. Somebody wasn't auditing for Linux kernel vulnerabilities when they found this. They literally were running into this problem with their log server, and you
And
know,
trying to figure it out,
it's
which is a huge pain. And a lot of this
yeah,
post is just about like trying to figure out and determining that, yeah, it's actually a kernel bug, not a bug in my own code. I do like the reproducer here, though, where he just wrote two programs, one that keeps writing A and the other keeps splicing B, and see if they end up interacting with each other to actually reproduce the bug. It's just so simple. Jumping back slightly, you just mentioned about the kind of the history of it and how the bug kind of came about, where this uninitialized use was like so long ago. It would be very easy for anybody who's just writing this code. Kind of the insidious part of it is like, writing all of the new code generally would have looked right. But it was because of this non-security bug introduced however long ago that it could be exploited. Like it's just such a kind of hidden place for the bug because all of the developers writing the code would have been fine. They wouldn't have necessarily noticed anything. Or like, code review wouldn't have picked it up. Well, would have picked up the uninitialized use, but not code review after that wouldn't have.
yeah. It was kind of multiple changes that opened up the exploitable scenario.
Yeah, which
Um,
makes it really interesting in that sense.
I do find it really fascinating that they had this uninitialized use in the ring buffer. Now, to be fair to them, and there was a bit of discussion about this in a Discord I'm in too, so I thought I'd bring it up here. Um, a compiler wouldn't catch this specific case. So, like compilers nowadays are pretty smart. They're going to catch a lot of uninitialized use. If you just have a stack variable that you never initialize and you reference it, the compiler is going to warn you about that. In this case, though, where it's in a ring buffer and they just keep reusing the memory slots, the compiler can't really detect that. So it is a little bit more of a subtle bug. That said, I mean, all you would have had to have done to prevent this attack is zero, like the ring buffer entry when you create or when you reuse that slot. Like you just zero out the structure and initialize what you need, which is the case in a lot of places in the kernel. Like it will do that explicit um, initialized by default. But here, that's not what happened, and they just never. I don't know. I guess because the flags field didn't have much use before, they just didn't feel the need to initialize it. But yeah, when that was later used for something important, that was a big problem. So it's kind of weird though, because even though the bug is subtle from a perspective of the compiler wouldn't warn you about it, um, and uninitialized use is a bit more of a subtler bug. I'm a little bit surprised that there weren't problems that were discovered that led to its discovery earlier than this, because they're just not initializing. Like as soon as they push that change in 5.8 where they use the flags, and they're never set up properly in the splice system call, like you would think that things would start breaking fairly quickly when you consider the scale that Linux is used on. So I
You
wonder
do
how
kind of
many
need
other bugs could have been caused by this that drove development teams nuts, and they just had to write like workarounds because they didn't go deep enough on the root cause.
what that's the thing, like you kind of need a lot of stars to align to one have the scenario come up, but obviously it does happen and did happen. But then at the same time, you also need on the developer side for somebody noticing this happening to also be able to figure out that it is the kernel. Like that isn't or that shouldn't be your first thought of, oh, this must be a kernel bug. Um you kind of have this spot where it's like, well, I can just keep an eye out for like, in this case, keep an eye out for the file having a bad, like write a script to just look at that, and all you would have to do is, just write a script to fix it, and you fix the problem even though you don't know the source of it. In a lot of environments, that's going to be all you do because it works and that's good enough. So, I mean, I could see this, I could see it having happen in other scenarios too, and just the developers either don't have the knowledge to dig into exactly why it's happening. I mean, not everybody's really going to dig into the kernel to kind of figure it out. Um, I don't know. I can definitely see this just, figure out some fix for it or some way of detecting it and just have a workaround without really even determining that was a kernel bug in the first place.
The other thing is, and I guess this is kind of a joke, but it's kind of not too, is this has only really been in the kernel since 5.8, which is like I think 5.8 is a little over a year old by this point, but a lot of people aren't really updating the kernels on their servers and stuff all that often. So there might not be that many servers or whatever that are running 5.8 for this to have been an issue. Because before then, like I said, the uninitialized use is there, but there's no security implications, or at least not any known ones.
Yeah, I guess
Um,
from 5.8, and I mean, it, is the current like new LTS 510, I think.
I think it's 510. Yeah.
Yeah, so I mean, we're not 510 would have been the first LTS that had it,
Okay, so technically,
or might
I
have
don't.
had it. I'm not even
I
sure.
don't think 510 LTS is it landed yet? I think 5.4 LTS is like the current one, and 5.10 is the next LTS, but I'm not 100% certain on that. Um,
Possibly, it might just be yeah. Okay, so it does indicate like a stable. Okay, that's not quite. That's not
okay,
LTS
yeah,
though.
sorry. So 5.10 is LTS. Actually, even 5.15 is LTS now. That was released on October 31st. So yeah, okay, I was a bit behind. I didn't think LTS had reached that high in the kernel versions, but it has.
Yeah, well, I mean, what was it, a couple years ago when they switched out to this much faster release cycle? Hard to
Yeah,
keep
they've
track of
really
everything now.
they really sped up the development cycle a lot.
Either
So
way, point is the exposure time on it. I mean, for a bug like this that you need to track down, a year doesn't feel like that long. Like, yeah, things could have broken, but it's really hard to track down and actually figure out that is a kernel bug.
yeah, and along the lines of what you pointed out earlier, with the fact that a lot of people aren't going to go digging through the kernel, the blog author kind of touches on that in this post, mentioning it's easy to want to blame the compiler or the kernel whenever you hit a bug in your application, but generally it's, people know that 99.9% of the time the bug is going to be in your code, not other people's code. But in this case, that this was the 0.1% case. So, um, yeah, like the kernel, it's easy to think of the kernel as like this stable oracle that you can just always rely on and never really care about. But sometimes you have bugs like this where you have to care about it and you have to dig into it to find it. Because yeah,
Or
I
you don't
really,
have to. You just have a
yeah, or you
workaround.
work around it. Yeah, that's true. But yeah, like something like this is like it's really hard to imagine a scenario where like a security audit would really find this, because you would have to be looking at a very specific area uh, with like the pipe buffer flags, and then go digging deep to find where that's actually useful to you for as like a corruption primitive. So yeah, really cool bug all around.
Yeah, it does
And
feel
yeah,
like
like
the sort of
pretty
bug that could
impactful.
maybe come up with fuzzing, although not many fuzzers would detect it as a bug. Um, I
Yeah,
can
because there's
kind of
no
see.
crash happening here. It's just data corruption.
Yeah, yeah,
So you'd have
that's
to
the
have a
thing.
special sanitizer for it,
Yeah,
basically.
yeah, you need to be looking for this sort of bug in what you're doing. You wouldn't like I could see it coming up from fuzzing. I can't see it being caught by most fuzzers.
Yeah, that's a good way of summing that up. So yeah, there is some more details. I would recommend anyone who this sounds interesting to check out this post. It does go through kind of a journal style, discovery of the bug all the way through the pain points and going through it. We've always kind of liked those style of blog posts because it shows gives some insight on the process and shows that this wasn't just like a day thing where they figured it out really quickly. This took a lot of like effort and pain to to get through, and you don't always see that in some of the posts that we cover. So uh, yeah, there's a lot of interesting information to read here, and it's pretty accessible. The blog does a good job of explaining what pipes are, some of the background there of what's necessary, some of the background of their application and what's relevant for the root causing. So yeah, I mean, it's a really well written post too, but yeah, mainly like the history of the bug is what's the interesting story here for sure.
Yeah, to me it felt a little bit long, but part of that is just completely on the style side. This is the developer writing the post. You get that all the time with their posts when it's coming down to like, here's how they triage and figured out this bug rather than being a vulnerability research post. So, like, I don't fault it for that at all, but it did feel a little bit long. You might be able to skip a little bit, a few parts of it to if you're just interested in the bug itself.
Yeah, you could probably skip a few of the opening paragraphs, especially if you're familiar with like uh memory corruption and a little bit about how pipes work. So yeah. All right, we'll get into our next bug here, which is a post from NCC Group on a Netgear Stack Overflow. Z, I'll let you get into this one because you looked at this one more thoroughly than I did, so I'll let you take this one away.
Before I do that, we'll also thank Balika for now 14 months of tier 1 sub. So thank you. And yeah, this bug from NCC Group, at its core, it's a pretty simple bug. It really just comes down to a basically unbounded copy into a fixed size buffer, which we have seen plenty of times before. Um, they walk through a lot of the first part of the post is some background on what is this. This is uh sorry, I forget the name of it. It was like I think a Netlink Netgear, sorry. Netgear router or system. You could plug in a printer for this ReadyShare plug-in USB printer. It'll put it out over the network as if it's a network printer. So that kind of explains some of the functionality that it has or the features. Ultimately, it'll read a request coming in, creates it off on its own thread. They walk through like the whole thing from the request to getting to the vulnerability, but it comes down to this response get jobs function where they will basically just read how much they'll read a 16-bit size from client data given some flags, some conditions. use that as the argument to memcopy, copy it into a 64-byte stack buffer. What I kind of want to call out with this post is less about the vulnerability, because that is really straightforward. Exploitation was also straightforward, but this is a stack-based overflow, but they have a lot of things. Let's see if I can find it on the post here. A lot of things sitting on the stack between where they overflow this command array, and then they overflow everything on there until they actually reach the end of the stack frame and where you've got like the return address. And so I want to call this post out largely for the reasoning of this kind of corruption of other stack data. I feel like it's, especially for people who are just learning, just getting into the exploit dev side of things, you know, you'll see all these tutorials about like, you have a stack overflow, you overwrite the return address. Maybe if it's on Windows, you overwrite the SEH or part of the SEH chain. But you basically just do that and you win that way. And more, I think the important concept is just understanding that you're overwriting whatever memory is nearby. Yes, that includes the stored return address. That includes, you know, the base pointer for the stack. That also potentially, and in this case, includes all of the local variables on the way there. That I think gets overlooked and isn't considered a lot of times. Granted, if you're doing plenty of exploit dev, you're looking at this. It's not anything crazy. Anyway, for their actual exploitation, they had a few things of interest in this. In this list, they had the prefix size, prefix pointer, and this is all reverse engineered code, so the names and stuff is just what they decide to give it. They didn't have symbols for it. And client sock is the third one. So what they found was, first of all, so this is kind of a network request, HTTP-ish request, or it might even be full HTTP. Either that or it looks like client sock, you might be able to guess, that is the socket or file descriptor for the client. And you have to overflow that. I guess that's the other thing. You are overflowing all of these things, so you do have to survive and not crash before getting to the return address also, even if you want to target the return address. So what they were able to do is they figured out that if client sock were an invalid value, the function would just return and you can kind of just go through the loop again with the connection. It wouldn't actually crash on that, so that actually let them brute force that client sock. The prefix pointer and prefix size was basically just what's the pointer to our, or part of the data that gets copied into the output buffer that gets sent out. So effectively, they're controlling both a pointer and a size that indicates the data that's going to be written out, which kind of creates this fun little leak primitive, because what they're able to do is you can point the prefix pointer wherever you want, say, yeah, there's totally like 100 bytes here that I want to read, and it's going to end up writing that out to your client sock, which you're able to brute force, just increment by one until it actually works. So kind of a fun case for getting that leak. Once they had the leak, they ultimately went with kind of a ret to libc style attack, just targeting getting a call to system with arbitrary data, rather than going for like a full ROP, because this is ARM 32-bit, so if you're not familiar with ARM, like on Intel and x86 machines, you have multi-byte instructions that are variable size. So you might have an instruction that's, I don't know, Spectre, do you know how long they can be offhand?
Oh, when you start getting into some of the extensions, you can have instructions that are like 10
They're
bytes long or longer.
13 was the number coming to mind. I just wasn't entirely sure about that. You can have some very long instructions, and inside of those, say 10 bytes, you might have other instructions. So ROPing on like x86 gets pretty easy because you have all of these instructions to pick from, and like you can parse them different ways. On ARM, they're all fixed size, so you don't have that choice. So it does quite substantially restrict the number of gadgets that you've got. So this, they figured, was an easier option. There was some ASLR in place. Not everything was randomized. There wasn't like Pi, or the executable wasn't randomized. There was NX in place, so they couldn't just like hop to their own shell code. Um, what other mitigations were here? Yeah, no canary, no railroad. So overall, not a whole lot stopping them there. What they ended up doing was they set the prefix pointer to the global offset table, had that basically were able to leak a bunch of pointers that way, have that sent out, use that to figure out the system. They found at the end of the function, basically they had a stack pivot gadget that they could use, which also let them sorry, I ended up skipping one step here. They had to get data in kind of a location that they knew. Um, and so on ARM 32-bit, mmap randomization was effectively predictable or quite broken. So having a large allocation would allow you to have a fairly predictable address, or just not terribly randomized. Um, so you can get that just by sending a large post, even though it's reading this data out into a fixed buffer. When it would read the whole request, that would happen into a properly sized and allocated buffer. So provide a very large request and content length header, and you'll get that mapped, and you'll end up having a somewhat predictable blob of data that you also control, and that could be used for this call to system. Once they know the address, overwrite it, and away you go. Fairly straightforward at that point. Again, it's not a super exciting exploit, but I did find at least this use of the client sock, doing a little bit of brute force there, doing kind of the info leak, all with this stack-based overflow. At least a little bit, I guess, refreshing in a sense. Like, it's just, I guess, using just a single stack overflow, not multiple different vulnerabilities to get their whole exploit. It's a nice setup,
Chaining
and
primitives with one bug, basically.
yeah. Yeah,
Um,
like, it's not an outstanding bug in any sense, but it is something that I think is important to keep in mind if you're just learning that, like, there's more than just the return pointer on the stack.
so jumping back a bit to your question, I was curious, so I looked it up. x86, the longest instruction you can have is 15 bytes. Anything beyond
Ah,
that is an invalid opcode. So
that was a couple bytes off. Oh well.
yeah. Um, Yeah, I mean, so there was a few points that I wanted to bring up with your point about stack corruption and just that idea of it. One thing you mentioned was this idea that you have to fake data, basically. You have to get local variables set to a certain thing, or you're going to end up crashing or hitting an error path or whatever. That is one thing that I feel is not covered very well in a lot of walkthroughs or CTFs or whatever, is just that idea of faking data, because it can be one of the most annoying parts of the exploit dev process, but incredibly important. A lot of like use after free tutorials or whatever will just have like these one field objects, or it'll be like one field and then like padding or whatever to make it fit in the cache that they want you to target. Um, and then yeah, you just overwrite like your one field that is actually used, and you're good to go, and you have code execution. Whereas in a lot of cases, your code execution target or whatever primitive you're looking for is going to be surrounded by a lot of other data, and how that's used can in some cases kill your exploit if it's like critical enough and you can't fake it properly. There's entire mitigations built around that idea. So it is kind of an important part of exploit dev that, yeah, just isn't really covered that well. The other thing that's important to think about when you talked about considering other things on the stack other than the return address, like, yeah, the return address is kind of the juicy target that most people know about and most people will try to attack. But because of that reason, it's also the target on the stack that's going to be protected the most often by something like stack cookies in modern applications that care about security at all. But stack cookies don't protect everything. So there could be some cases where you have a linear buffer overflow where you can't exploit it by attacking the return address because of the stack cookie and you can't leak it or whatever. But there's other data on the stack that could give you other useful primitives. So that's another reason that it's important to look at some of the other things on the stack too. But yeah, I kind of agree with you. I think the bug here is fairly like straightforward, nothing too interesting there. But the exploit strategy is some it covers some things that we don't cover super often, and doesn't show up often in sort of the more beginner focused material either. So I think that's a fair shout.
Yeah, I think it's, it's an educational reference, really. And it's a well done write up, too.
Yeah. Getting into something that's a little bit less beginner oriented, I guess, we have a security analysis of MTE by Sarah Mar. This came out of Blue Hat IL 2022, and it's centered on an analysis of memory tagging or MTE. So before going too much into the meat of the slides, I guess we'll talk a little bit about what MTE actually is for those who aren't familiar with it, because it's not very commonplace
Well,
yet.
before you, I guess, do that, actually, I will say, like, as a post, this actually, or sorry, as slides, it's pretty solid. And it does include a lot about how memory tagging itself works. Like, it starts off just talking about what memory tagging is. So I'd say that discussion is partially going through the slides.
Yeah, I'd say like the first half of the presentation goes into the background, and then the second half into the examples. So yeah, MTE is basically, you can kind of think of it as hardware address sanitization. Pointers have tags that are embedded in them, which are verified and checked by the CPU whenever there's like a load and store or whatever. And if those tags don't match the shadow mapping that the CPU cross references, it'll trigger an exception and crash, which is a pretty effective exploit mitigation because a lot of the time in exploitation, your end goal or one of your building blocks will involve smashing a pointer or overlapping different pointers or whatever. Um, so memory tagging is kind of designed to keep pointers isolated from each other in a sense. ARM has two modes for MTE, synchronous and asynchronous. Synchronous, as you would expect, it basically guarantees the exception is raised upon violation of the memory tag, but it's less performant because it has to wait on that verification before it can actually perform the load or store. Asynchronous makes it so whenever a violation occurs, it sets a flag in the tag vault status register, which the OS needs to periodically check. But an instruction that would have an invalid or improper memory tag will still execute. So it's faster, it's more performant, but it's also less secure because you give an attacker a bit of a foothold there and a bit of a window where they might be able to do something before the exception is caught or handled. So depending on what your needs are as an application, you can kind of configure and make that trade-off however you feel is necessary. That is one thing that's kind of cool with how MTE is implemented on ARM is it's pretty configurable in that sense. Um, it's worth noting you can still get around memory tagging and play nice with it in an exploitation scenario, assuming you can leak the tags, or if you can try to fake a pointer to memory that's marked as untagged memory, which I assume might be necessary in some cases for like memory mapped IO, if you're talking about kernel, for example. So, memory tagging sounds scary, and it is scary in some respects. It is suspected to it people are expecting it to kill at least a few different bug classes and types of corruptions,
There's
for the
definitely
large part, but
there's
it is,
the
there are ways around it.
yeah, there's the definite potential for it to do more. As it stands, how we've seen it actually land, we haven't quite seen that. I think the strongest landing of it has been the Cherry devices, which we talked about a couple times when we've dealt with the Morpheus chip and kind of doing it there. But as it stands with how it's so this is actually, I've talked about doing a update on our the future of exploit development, because I think when we were doing it just as MT was starting being worked on, and like we are just getting some chips landing with it, similar with Intel CET just landing. Now that we've kind of seen them land, seen where they've gone with them and stuff, like I'm feeling a bit more optimistic than I was at the time that we recorded that video. Um, and this is just kind of another continuation on that, where there's some potential damage that comes from this. Like, this does cut out certain class of bugs, and they go into like how some of the mitigations that can actually be implemented using memory tagging. The memory tagging itself doesn't necessarily need to be a security thing. Obviously, it's going to be implemented as that, but it's just like an architecture feature. One of the things they talk about is like having heap safety on it. Well, I believe they have a page that just kind of talks about a few attacks, which you are just about to get into. I'm
Yeah,
just
so I
trying to
think on
find it.
slides 28 and onward is where they have kind of a table of some of the bypasses or uh, ways that you can get around MTE. So, like for example, if you know the tag or can leak the tag, it's kind of useless. So you can embed the tag in your pointer and you're fine. Or you could corrupt the least significant bits of the pointer and keep it within the range of the block uh, for that area of memory. Sorry, go ahead, Z. I think you were going to comment on this table, though.
Yeah, no, I was basically just going to call it out and go over it here as you just were. Like, you had just mentioned before I first cut you off with being able to fake a pointer into untagged memory. The other thing is corrupting the least significant bits, kind of keeping it within the same region. Just intra-object corruptions in general aren't really going to be dealt with. Information disclosures can disclose, yeah, the tag, because the tag is still part of the address. They're using the upper 4 bits of the address as like where the tag belongs. So it is part of the address. It's not like outside. It's still going to be leaked in the same way. You're still able to take advantage of things there. And then they talk about type confusion. And they actually had, this is the first time I've actually seen uh where is it now? Yeah, first order type confusions. Uh, First time I've actually seen somebody using that phrasing for it. Makes sense, but just I hadn't really thought about it in that way before. As being basically, this also doesn't do anything when it comes to first order type confusions or type confusions that are like directly in the code, where it's just using the wrong type, versus second order, which is where you would corrupt something and kind of cause a type confusion because of your corruption changing the object that it's going to treat it as, or like changing out a pointer or something like that, so it's pointing to the wrong type of object, things of that sort. And I don't know, it does call out that type confusions, first order type confusions, tend to be a minority of the bugs like you've seen in the past years. They have been. I do feel like type confusions are growing, and part of that kind of comes down to they're hard to detect in a lot of cases because there's potentially, valid data being used. Oh no, I feel like part of the reason they're not popular isn't so much that they don't exist, but rather just the fact that we don't have good ways of detecting them. I mean, there are some better ways now with ASAN and stuff over the last few years, but I feel like there are easier targets, and that's just why type confusions haven't been getting hit as hard, rather than the idea that they don't exist. In fairness, they don't say like, they don't exist, just the pattern is they're not, or they're a minority.
I was just about to mention that. I think the thing with type confusions is to spot them, you have to have a more intricate knowledge of the code base than you have to have for finding some other bugs. So I think it's just one of those things where looking for other bug types is easier and currently makes sense. Whereas the meta could shift more towards trying to find type confusions when some of those other bug classes are killed off or become less common. So
Yeah, and I guess we should also call out, while saying that type confusions aren't as impacted, what is impacted and what does kind of matter here is this does deal with those kind of linear overflows and underflows, because you end up having a pointer, you overflow, you end up outside of the tag range, and you should end up in another tag. Like the tag should be changing for adjacent memory. You shouldn't have two pieces of adjacent memory back to back. So you end up overflowing into that, and you kind of lose the ability to, well, do that basically. So it does have some significant impact with some bugs, and these memcopy style bugs, like the one we were just talking about in the last post, that would have been much tougher to exploit. That said, you would also need uh this to be done on the stack for the one we were just talking about, that memcopy. Um, Versus the heap. A lot of this does focus on protecting heap data versus stack. A little bit harder to implement it there. But one thing they do also call out here is that one place where this will help is in just running this at scale. You know, your phone can have MTE on it. You're just running random applications, causes a bug report while you're just running it. So now suddenly everybody is like running a lightweight version of ASAN with everything they're doing. That can definitely find some more bugs that would have otherwise remained hidden apart from somebody like doing fuzzing or what or reviewing for it.
So there were a few examples that were covered in the slides that kind of demonstrate some of the bypasses that were mentioned or the techniques that were mentioned in the earlier slides. Example one was from Project Zero and NSS, which was a linear buffer overflow. Again, this kind of focused on that idea that you can just corrupt bytes inside of the same like block of bytes because sorry, I don't remember if either of us mentioned this earlier, but one of the weaknesses with the current MTE implementations, at least as we've seen it in the Linux kernel, is the granularity is quite small. Um, so I think it's on the order of like 16 bytes. So a tag will protect 16 bytes, but yeah, they want to keep memory overhead low, so the granularity is fairly large still. Um, so as long as you're within that 16 byte slice, um, you can shift some pointers around inside of that, or just corrupt data that you shouldn't be able to control inside of that slice, and you won't trigger MTE. And example one just kind of talks about that. Another example was a JavaScript core bug in WebKit from 2018. This was a type confusion from Salo. Here the slides go a little bit into the fake obj and address of object primitives, which we've talked about before and when we've covered browser bugs. These are the primitives based on using a type confusion between an array of objects and an array of doubles, kind of getting overlapped view on them and using the array of doubles to either inject fake object pointers or pull real pointers of objects that are stored there. And Saramar goes on to detail that this type of confusion wouldn't really be impacted by MTE because usually with that, when you're getting those types of primitives, you're just expanding the size of an array. You're not really messing with the pointers. So MTE can't really do too much there, I don't think. The final example went into a little bit more detail, and this was a CTF challenge from 0 Points, CTF 2020. I'm not going to go too deep into it here, though there is a blog post that's linked in the slides for those that are interested. Basically, that challenge had a type confusion with a list of elements. When you went to edit or add an element to the list, it would just ask you for the type, and you could specify whatever you wanted. So very like exposed bug. The challenge was more on the exploitation than it was on finding the bug. The arbitrary read they got for free basically with the get functionality. Arbitrary write was a bit trickier. They had to get an arbitrary free primitive in order to get control over less list data to get an arbitrary write through malloc, and that was just like attacking DL malloc, attacking forward and back pointers, kind of the common heap corruption type stuff. The arbitrary free was used to free the list and get the data pointed to stack to get a bit of the stack corruption primitive. Um, when you throw MTE into the mix, it complicates the exploit strategy, though, particularly on the arbitrary free, for example, because you need the right tag for the list allocation. Otherwise, you'll crash, right? Because you'll retag it, but you won't tag it with the right value. Basically, the solution there was to leak the tag, I believe, by using the arbitrary read to scan the stack, since they know where it is in this challenge. And the main stack frame has a pointer that you can kind of leak the tag from. So yeah, I mean, there's a lot more here for that example and some of the other stuff, but I won't go into it all because there is a lot of slides here and a lot of detail. Um, but yeah, I mean, there's not a lot of resources on MTE, and I think these slides and this presentation does a really good job of just kind of um, pulling everything together and showing you, like, here's what MTE is, here's what its weaknesses are, here's some techniques that can be used to get around it, and here's like points that need improvement, I guess, on it. So it's just I think the slides are good for if you want to learn about MTE. If you think that an MTE is going to come to a target that you're looking at, or you just want to be up to speed on it, I think this presentation and slides do a pretty good job of it. So
Yeah, like just the slides, it's a really good presentation. I do look forward to actually seeing the presentation itself if Black Hat puts, or sorry, Blue Hat, I made the same mistake as you. If Blue Hat puts it out, which they may or may not. Blue Hat will publish talks given that the presenter okays it. But they usually take a few months before they actually get him out. Anyhow, given the fact that he's put out the slides, I assume he's going to be fine with putting out the presentation too. So hopefully we will get it. In the meantime, I will also call out a talk from the Linux Security Summit that happened back in October. And that was about implementing memory tagging in the Linux kernel. It goes into pretty reasonable depth about some of the trade-offs they made with how they decide to implement it. Just a really good presentation also, if you do want more kind of information on memory tagging beyond just the slides here.
Yeah, that presentation did a really good job of highlighting the shortcomings and whatnot too. So definitely a fair shout and a really interesting talk. I don't know. This isn't really related to the contents of it, but I thought it was kind of cool. This was obviously when you know things were still shut down. The conference couldn't happen in person, so Andre kind of went to like different locations in real life and gave like the presentation in different spots. So yeah, just a really well done presentation too. So yeah, I'd recommend checking that out too. But yeah, did you have anything else you wanted to say on the MTE stuff? See, or I guess
No,
we'll
I
wrap up the show.
think we're good.
All right, cool. So that's all we have for today. Thank you to everyone who tuned in. The VOD will be up on YouTube and Spotify and other platforms tomorrow. Feel free to follow our Twitter and join our Discord for notifications for when we go live and for discussion. We'll be back next Monday and Tuesday for the Bounty and Binary episodes, respectively, and we'll see you all next week.